whatever. You can work on that differentiation pattern. So for people who are in my 8th period class yet are not here right now, you are dead to me. But I guess legally I'm supposed to continue teaching you, so we are recording a video. And the video is, first we're going to go over the homework on parametric equations. How did that go? People who are actually here. On last Friday we learned about the calculus of parametric curves. And we had some homework numbers to do. I can't remember the exact problem, but it was like page 725, and it was like maybe 8, 14, 24, 33, 39, maybe. I'm just making up these numbers.
1 and 9 and 34.
34. I didn't actually hear you. Was that close enough?
9
okay, good.
9.
Good. Which of these should we go over? Let's go over like 3 or 4 of them max. I don't know, what do you think? Or who? I could just pick some if you would like. Okay, we could just do number 9. We could do
I think like 1 of 33 or 34.
Or maybe 14 is more exciting. 14, 30.
1 of 33 or 34.
Okay, let's do 33, and let's do 39. That sounds pretty good, but I can do all this upon request. While I'm doing this, could 6 people go put the anti-differentiation bookwork problems up that Daniel Schaefer has curated for us?
I didn't do a good job dividing up space.
That's probably sufficient space. Okay, number 14 gave you the following pair of parametric equations. X equals theta minus sine theta, y equals 1 minus cosine theta. And the directions were to find dy dx at theta equals pi over 4. No, at theta equals pi rather. And also to find d squared y dx squared at theta equals pi. Okay, so we begin. Well, to find the slope of the tangent lines of the curve, what I'm interested in is the instantaneous rate of change of y with respect to x. So if I want a formula for dy dx, as we learned on Friday, that is just dy dt over dx dt. And the reason, for those of you who are playing with robots, is it's just a chain rule, really, right? Also, it's just sort of common sense. Right? The instantaneous rate of change of y with respect to t over the instantaneous rate of change with respect to of x with respect to t is the rate of change of y with respect to x. Okay, derivatives just act like slopes. Okay, so that means we just do it. Also, in place of t here, I guess I should be saying theta. The variable is not relevant. Okay. So what is dy d theta? I just differentiate this. Derivative of 1 minus cosine theta is just sine theta, yeah, it is, over dx d theta is negative cosine theta. No, it is 1 minus cosine. 1 derivative of sine is, yep, good. So, having done that, I can now do the other thing they said to do, which is specifically to find dy dx at theta equals pi. And I think this turns out to be silly because you just get 0. Not silly, but what that means is that this curve at theta equals pi has a horizontal tangent. Okay, good. Now comes the slightly harder part. I want to know this d squared y dx squared thing. What is that? Well, that means the derivative with respect to x of dy dx. And if you really understand what's going on here, you should see that as meaning I want to know, with respect to x, the change in dy dx, which is kind of like saying, yo, I want to know, this is sort of like saying dy dx, dx. And by like sort of writing it like that and thinking of it like that, you should realize that this is almost the exact same thing we just did. Because dy dx is a function of theta. In other words, there's a formula. In fact, this is the formula for the rate of change of y with respect to x for a particular angle theta. And so we're really just differentiating that formula with respect to x. In other words, it's the same thing that's going on here, right? Here we're differentiating y with respect to x, and so the answer is, since x and y each depend on theta, dy d theta over dx d theta. Here, since we're differentiating dy dx with respect to x, and each of these are independently functions of theta, I don't know if this conversation is helping or not, but then the answer is that this is the derivative with respect to theta of dy dx over dx d theta. We're saying if you just like totally get this, like the lesson the first time around was good enough, or you read the book-ish. Did this help, this little explanation of the last 3 minutes? Sort of just, I'm trying to show the parallelism between what we did here and what we did here. It's really the exact same thing. As soon as you understand that dy dx is itself an expression which depends on theta. So it's just operating at the same role as like kind of y is. I don't know. Okay. Anyway, now we do it. What is the derivative of dy dx? Well, I just simply need to take the derivative of sine theta over 1 minus cosine theta, and on the bottom I need to do dx d theta, which I already did. It's just it's 1 minus cosine theta. Okay, so what is this? I guess I'll use the quotient rule. Derivative of the top is cosine times the bottom 1 minus cosine minus, so that's minus the top sine theta times the derivative of the bottom, which is also sine theta, over 1 minus cosine theta squared. But really that's all over another 1 minus cosine theta. Right, and I think this numerator simplifies nicely because it's like cosine theta minus cosine squared theta, but then minus a sine squared theta over, and then this is 1 minus cosine theta cubed. You guys following all this? But then that's just another trig identity can happen right there. So that is actually like cosine theta minus 1 over 1 minus cosine theta cubed. And that is just the opposite of that. So I cancel one of those with a -1 residue. Alright, so this is -1 over 1 minus cosine theta squared. That is the formula. This is number 14, answer not in the back of the book. Raise your hand if you did this entire problem and you got exactly this. Okay, that's some hands. People who didn't get this, what happened? Okay, alright, so now this is the formula for this in general. So now I want to, because they asked me to, I want to do this at theta equals pi. And when I plug in pi for cosine pi is -1, so 1 minus -1 is 2, so this is -1/4. What's the significance of that -1/4? It means that the slopes of the tangent lines are decreasing at a rate of -1/4. That means that this curve must be concave down near at theta equals pi. All right, that was a good all-around problem. Let's do just like 1 or 2 more. Turn 3. This is a nice problem because you already know everything there is to know about this guy. X equals 4 plus 2 cosine theta. Y equals -1 plus sine theta. This is a pair of parametric equations. What is it? Immediate responses from all students in the room shouting with
What?
the answer. What is this? What is this?
A curve.
What curve?
Parametric. Parametric.
Is it an ellipse?
What curve?
Is it an ellipse?
He knows, right?
Yeah. Is it an ellipse?
People watching at home on the internet, let the record show that 20 seconds has gone by. Yeah.
This is something that has to do with like cosines with x and the sines with y. So it's,
Yeah. It's an ellipse.
Yeah, it's definitely an ellipse. It's definitely a thing that we learned, like,
Marginally more.
I know, it was 10 or 15 years ago that you guys learned this, so it's understandable that you were so yeah, duh, right? What is x? X is something which has been moved forward to the right, and then is waddling back and forth with amplitude 2. Y is something which has moved down 1 and is waddling up and down with amplitude 1. Of course, this is just an ellipse, right? And in fact, we even did crap last semester with this, where we just easily algebraically converted this into this standard form for ellipse by saying, yo, x minus 4 over 2 is cosine. It's coming back to you now. Let's go, yeah, and y plus 1 is sine. And then since sine squared plus cosine squared equals 1, then you in fact have x minus 4 squared over 4 plus y plus 1 squared. You can write over 1 if it makes you feel better. Boom. Alright, so that's like already, this is already like a recognizable pair of parametric equation. So that just means you have an extra check on all of your results. So we go over 4, down 1. I'm just making a little graph of this right now. Why not? Major axis length 2, and minor axis 1. Alright, so I kind of just like already know what to expect. That there is going to be this point here at 4, 0, this point 4, negative 2, this point 6, negative 1, and this point 2, negative 1. Alright, let's see what calculus has to say about this. The directions for this problem were find all points, if any, of horizontal and vertical tangency to the curve. Okay, we do it. Well, first I can calculate the slope dy dx, which is, again, dy d theta dx d theta. dy d theta is derivative of that is cosine, and dx d theta is negative 2 sine. Yep. Okay, so when am I going to have a horizontal tangent? Answer, when the slope of the tangent line is 0, which happens when the numerator is 0, which happens when cosine theta equals 0, which happens at pi over 2 and 3 pi over 2. Theta equals, theta equals. Okay, well when theta equals pi over 2, where am I? If I just plug in pi over 2 here, I get 4. And if I plug in pi over 2 here, I get 0. And when theta equals 3 pi over 2, I get 4, comma, sine of 3 pi over 2 is negative 1, so it's negative 2. Good? Say good. Are we still like in frame and stuff? You're like keeping track of that?
No, I wasn't, but yeah.
Where'd you go?
Very
Who was in charge of this? Yeah, are you like in charge over there?
You said not, don't touch it.
Yeah, but if I'm out of frame, then you need to touch it.
No,
I mean,
no, you're still there.
generally monitoring that I'm in frame at all times. Yeah, good. All right, good. And then, do we have, oh, by the way, that's exactly what we saw down there based on making the picture in common sense. Do we have any vertical tangent lines? Well, I'm going to have a vertical tangent line if the slope is like infinity, right? Which would happen when the bottom is like basically 0. So that is happening when sine theta is 0. So that happens at theta equals 0 and theta equals pi. And where am I when theta is 0? If I plug in 0 for theta, cosine theta is 1, so that's 6, negative 1. And if I plug in pi, cosine pi negative 1, so I get 2, negative 1. So everything matched up to exactly what I thought it should be based on like knowing things. Cool? Say cool. All right, can we stop or do you want to do one more?
We can stop.
Stop? Everyone got 39? I thought 39 was tricky, but I'm ready to just move on. Okay, good. Before, I can possibly do one more, but before, everyone take a minute and check your answers to the anti-differentiation problems from the textbook. I thought that they were, generally speaking, easier than the ones we were doing in class. So hopefully that was like good. And they each take like, I don't know, like a minute or two. Those are some. Everyone check your answers. How'd it go, generally speaking? What does that mean? Okay, good. So who says okay? Alright. Everyone feeling good on the parametric stuff?
Yeah.
Feeling good on anti-differentiation? Please, how's it going?
Great.
Good. Alright. You people at home, 1, you're dead to me. 2, did I mention that? Yeah. 2, you should make sure that you know how got all the answers to the odd numbered problems from the anti-differentiation homework. Answers are in the back. Woo! Alright. Can you take out the packet on anti-differentiation? Do you not do anything? Like you didn't catch up or anything or print it or anything? No?
Wow.
I mean, how we stand up.
Accusations.
Okay, those of you who are not here because you were playing with robots, you missed an entire like 45-minute plus lesson on anti-differentiation by the method of substitution. So try to catch up. Who else needs a packet? Raise your hand high, turn around. Good. All right. So I thought these problems were significantly harder. We did a bunch of them together. Everyone first just like take a minute and compare to the person next to you and figure out how it's going, and then we'll do a couple together right now and we'll work on this for a bit. I'm going to do 19.
Either it's really gross or the way it's really gross is a better way to do it.
Okay. One half.
You know, like when, okay, so substitute you for something that is like, they're, like, you look at the, you might notice you change the like, an x cubed, there's x squared, and there's like, and then you're like, okay, this is all method.
So they're like all the same. Videos from me. From you and the videos. It's basically all the same. Do you think? This one's the difference is that you solve it. That one's the difference is that you don't do the thing where you have that one half.
You kind of look at it and you can make it.
Don't
worry about it. Mr. Ray says he does this one. He says something like this.
Be like, then you have to once you're at the end here, it's basically just du. You already know what it is. So,
Wait, I'm sorry.
Negative 23rd. This?
No, the like. Or
Right. So it's like when we do.
Isn't this du?
It's like,
Oh,
okay. Also like the way you think dy over dx. It's like you're saying when we do our d over d.
All right, let's do a couple of these. Which one should we do? I feel like we should do 18 maybe. Oh, you didn't try these. You said to do through page 4. Through page 4. Guys, there's a lot of homework that was due today. There's a lot due next class. There's a lot after that. And there's a lot more after that. We're just going really hard. So keep up. This class is about to get really hard from now until like June 1st. And the last 2 weeks is kind of chill. But the next 3 weeks is really hard. All right, so good. Shall we go over some of these? Everyone can do these. Some people just figure out how to do it very, very, very quickly. Other people struggle, but the more of these you do, the easier it gets. So the solution is just practice, practice, practice. Fortunately, your wise overlord will be assigning tons of homework, so you'll just get better and better and better. All right, antiderivative of sine 10x times e to the, no, cosine 10x, right? No, sine 10x. Times e to the sine squared 10x. No, 5x.
I understood last time.
Yes. All right. How should we do this? When you look at this, what's the first thing you notice?
It looks like there is.
Does it look like some chain rule happens here?
Yes.
Like maybe, like not obviously, but yeah. What?
Can I make a suggestion?
Please.
So you have like a sine of 5x.
Yeah.
You have a sine of 10x.
Yeah.
But if you try hard, you can get a sine of 5x out of a sine of 10x and like.
Yeah, this was like a pre-calc B thing, right? You would have an equation, a trig equation you're trying to solve. Like it's hopeless if the arguments are not the same, right? But sine 5x and sine 10x are related to each other via the double angle formula. So it's like very suggestive that we should use the double angle formula for sine to rewrite this in terms of sine 5x. Okay, if we do that, what is sine 10x? Well, it's just like 2 sine 5x cosine 5x times e to the sine squared 5x. Now we're looking good. Because now, this is more obviously looks like some chain rule happens here. Because what is the derivative of sine squared 5x? Using the chain rule, derivative of sine 5x squared, that's like 2 sine 5x. Back in sine for the derivative of sine 5x, which is cosine 5x times 5. Yeah, so if I let that be my u, then everything is going to work out. So you may not have seen immediately to do this, but this is the way that will just work. If you let u be sine squared 5x, then du dx is, if I differentiate this, I get 2 sine 5x back inside for the derivative of sine 5x, which is cosine 5x back inside 5. And therefore, this du is just like 10 sine 5x cosine 5x. And that's almost exactly what I have here. I'm just missing the, I'm missing the 5. All right, so I stick in a 5 and I undo the damage with a 1/5. And now I rewrite this antiderivative in terms of u's. So this gives me 1/5 antiderivative e to the u du. Boom. And now I just do it. Yo.
Why did you choose to make u just sine squared with 5x rather than like e to the sine squared?
Because if I let it be e, but let that be u.
Still would have worked. It still would
That
work.
would have worked too?
You would have just gotten it.
Literally,
It would have been the antiderivative of du.
Yeah.
Oh, no.
Yes.
This just seem easier. You have to do more chain rules your way, right? Or no? It ends up being the same thing. You would get just a du.
Yeah.
Like, hold on. Yeah, that works too. But this to me is pretty easy, right? I mean, so because what is the antiderivative of e to the u? It's just e to the u. So the answer is 1/5 e to the u plus c, but the real answer is 1/5 e to the u is that, so it's e to the sine squared 5x. Ta-da! Okay, I thought 19 was the one that was really hard, so we should talk about this right now. If you didn't do it, it's just really, really sad because I'm about to tell you how, and so you'll never be able to do it yourself, ever. Here we go. X cubed plus 1 over x squared plus 4. What should we do? What did we talk about last class in situations like this? You should do polynomial long division, yeah. Whenever you can do polynomial long division with a rational function, you should, because it will split the rational function up into little pieces, and then we can anti-differentiate them individually, and that will reveal this thing for what it truly is. Okay, so if you haven't done this already, you should do it right now. Off to the side, get ready to do a little polynomial long division, and it's not even really that hard, because this goes in x times x cubed plus 4x. Am I like in framing stuff? You have to tell, you have to like keep moving the camera. Yeah. No, it's better if it's just one person in charge. Okay, I'll pay you with an orange.
Whoa.
Yeah. All right, good. Anyway, we are then we get negative 4x plus 1. Okay, cool. That means that this problem is really, this entire rational function is really just x plus negative 4x plus 1 over x squared plus 4. Alright, everyone should have gotten that far because we talked about this last class as like the thing to do. Alright, so now how am I going to deal with this? Well, the good news is I know how to anti-differentiate x. It's just x squared over 2. So now I just have to figure out how to deal with this other mess over here. And at first, I'm hopeful that it's going to be easy because after all, I have a quadratic in the denominator and I have a linear function in the numerator. And the derivatives of quadratics are linear functions. So if this numerator were the derivative of the bottom, give or take a constant, then I would be really happy. But it doesn't quite work. Because the derivative of x squared plus 4 is like just 2x. And so it makes me sad because there's this 1 here which is like ruining everything. If it were just 4x, then it would be good. Does everyone see what I'm talking about? Or no, Blair, what do we do?
Just split it.
Split it up even further, she says. She says, all right, look. Blaine's like, look, why don't we just say, all right, well, this is negative 4 times the antiderivative of x over x squared plus 4. I can handle that. And then just like plus the antiderivative of 1 over x squared plus 4 dx. In other words, by like maximally splitting up the fraction, I now think I can handle at least more of this problem. How do I do x over x squared plus 4? We did problems like this in class last week. Yeah, with logs. I will let u be x squared plus 4, and if u is x squared plus 4, then du is 2x dx. And that's good because that's more or less, give or take a constant, what I have up here. And so I stick in a 2, and I undo the damage with a 1/2. Is everyone following all this? Alright, so this really becomes minus 2 times 2x dx is like my du, and x squared plus 4 is u. Cool? Okay. And what is the antiderivative of du over u? It's like ln absolute value u. Except you don't need the absolute value because u is just x squared plus 4. Alright, so now I'm like 2/3 done with this problem because I've split it up into 3 pieces, 2 of which I've been able to take care of. Sound cool? Alright, so now all I have to do is figure out what the antiderivative of 1 over x squared plus 4 is. Okay, what should we do? Yeah.
It almost looks like the derivative of the derivative of arctan.
It almost looks like the derivative of arctan, he says. Yeah, because the derivative of arctan is 1 over x squared plus 1. So it's like, oh man, you stupid 4. I wish you were a 1. Well, we can make the 4 a 1 by the power of positive thinking. Also algebra. We can just make it a 4 by just factoring out a 4. So we just do that. This is what you guys are telling me to do? Something like that. Yeah. So on the top we have dx, and on the bottom we have just take out a 4. And then this is x squared over 4 plus 1. And now it's looking very arctan-ish because, well, this 4 can just come right out of the antiderivative. And then there's about one more sort of smartish thing I need to do. So this is like 1 over... the problem is it's like x squared over 4 plus 1, so I have to like, yeah.
X squared over 4 is x over 2 squared, so you can represent it as the derivative.
Please says, yo, x squared over 4 is really just like x over 2 quantity squared, and now it's looking very arctan-like. All I have to do is substitute for this variable. How's it going over there, Rich Costa? You do all this already? Yeah, good. So now we let u be x over 2, du is 1/2 dx. I need there to be a 1/2 in there, so I stick in the 1/2, I undo the damage with the 2, and I really have 1/2. 1/2 dx is du over u squared plus 1. And now I bask in the warm glow of arctan. That's just arctan, right? So I did all the hard work, and the answer here is 1/2 arctan u. But u is just x over 2, so my actual answer is x squared over 2 minus 2 ln x squared plus 4 plus 1/2 arctan x over 2 plus c. Alright, raise your hand if you figured this out by yourself before class today. Okay, raise your hand if you get it now. I guess that's what's important. Just kidding, that's not what's important. It's also important to try the problem at home by yourself first. Good. Alright, more. Let's do more. Let's take about, I'm going to set this alarm for, what's halfway through the period?
Miles.
Like 45?
So that they can get.
Yeah, like 45.
Yeah, okay.
So let's spend 13 minutes right now doing more of this packet. Everyone try number 20. Go.
Hand, sign, and
Probably.
That's
It's gonna be one of those.
Tan, sine, and secant are like positive. The ones that start with C have a negative sign.
Good job.
Wait, no, you can't.
Secant
Oh,
is
you're
like,
too cute. I'm sorry.
secant 10.
Alright, this problem's actually really easy. What do we do? It's just arc sine. Yeah. David Bang would like to remind us that the derivative of arc sine is 1 over root 1 minus x squared. And so this is basically that. I just rewrite 4x squared as like 2x and then I like you stuff it out. Okay, good. 20 is boring. Let's skip that one. Let's do 23. That was pretty hard enough to be a challenge for us. Yeah. Challenge. Everything. You really just need to like go on that line and do all of them fast. I sent you a million videos before you're done. Really need to like it's really terrible. My new world order, I'm just canceling all field trips. Changing the school mascot to a panda.
Can you at least make the school's mascot not sideways abs?
Sideways abs.
Yeah, like there's like a mural of it at the gym for like the abs or something.
Yeah, the six pack is like sideways.
Yeah, it's like 3 by
3 columns of 2.
Yeah.
Alright, does this number 23 look like anything to you? Wait, please do number 23.
You gotta take the X out.
Yeah, I did.
And then you have the R. What is it?
Nope.
Oh.
Yeah, 23.
Once you see it, but before you see it, you don't see it. Alright, some people tried to like do some factoring thing, but really that doesn't lead anywhere. This really goes back in some deep way to like Algebra 1 or something like that when you learn there's really only one parabola, y equals x squared. Every other parabola is just some like shift or stretch or whatever of that real parabola. And so to truly like understand a quadratic function, you need to like write it in its like natural form that it wants to be in, and then it's just like clear what it is. Who knows what I'm talking about? I'm talking about completing the square. By completing the square, you can reveal the quadratic for what it truly is. And so let's do that right now. You may not have completed the square in a while. Well, it's right there in your brain where you left it. What should we do first?